The resistance involved can also be found two ways. First, you find the short circuit current. You find the open circuit voltage. From that, you can find R Thevenin also. Okay. Then there's a third way of finding R Thevenin, which is called it. What is the third method for when you have dependent sources? What is the third way of finding the Thevenin resistance? A test signal method. Okay, let's go through that with an example. And the example I have in mind is also from the textbook. Not exactly the same as that one over there. 2 amps going here. And then a dependent voltage source, 2Ix. And this grounded to be potential 0, 2 ohms. And then you ask yourself what the open circuit voltage is. And this is equal to 1 ohm. And this is the current flowing in this direction. And this dependent voltage source is dependent on this current that flows over there. Okay. So this is V, and this place here should be V minus 2Ix. And we solved this circuit in class before. Okay, and it was quite easy to solve. And from this, you can find the open circuit voltage. And that open circuit voltage will make this into V becomes V Thevenin. Is the open circuit voltage when you don't connect anything across this one. Okay? And then if you want to find the short circuit current, you put a wire short circuiting it, and you solve this problem again. Okay, that short circuit current should be I Norton, right? And I'm sure that you know how to solve this problem. We went through that in class in the last lecture. Find I short circuit. Okay, then I Norton is I short circuit for the second problem. And then you will have R Thevenin, which is V Norton divided by I, V Thevenin divided by I Norton. Okay, I think we can easily prove this. Okay, we can easily prove this. I think so, yes. We can easily prove this. Okay? And then, after having done this, then there's also the source suppression method. Source suppression method means that you turn off the sources in that circuit. But unfortunately, if you turn off the sources, nothing happens. And then if I were to turn off the sources, I will have an open circuit there. I will have a resistor here. I will have a dependent voltage source here. And then I have something like this. Okay? And then if I look at this circuit, I suppress the source. Okay? But this is a very strange voltage source. It is a current-dependent voltage source. And the current that it depends on is this current. And that was 1 ohm over there, right? 1 ohm and then 2 ohms. So I cannot get this dependent voltage source to work unless I send a current in there. Otherwise, I really cannot know what resistance does this have. So I have to send in a test signal. Okay, for this, because there are dependent sources in there, I have to send in the test signal. So I send in the test signal, I, and then send it in there so that this thing will become responsive. Otherwise, it does not respond. If there's no current, nothing happens and nothing flows, and you cannot really define a resistance. Okay, so you want to see what kind of resistance you have when you look inside this way. You put your big eye looking in that direction. What do you see? You don't see anything unless you send in a current. Right? So for dependent current sources, you have to send in a test signal. And this problem was easy enough to solve. I think all of you knew how to solve it. And from that, you can find RT. Okay? Is this clear to everybody? I have RT being 1.2 ohms in my note here. Okay, I hope you get the procedures clear in your head so that you can actually go through these procedures and understand when you need to send in a test signal. Okay? Are there any questions? How many of you know linear algebra? Okay, so all of you know linear algebra, which is good. Maybe a large majority of you know linear algebra. I see a lot of hands. Maybe some of you are shy, so you don't put up your hands. So maybe a majority of you know linear algebra. So maybe I can take the remaining time proving this concept. I don't know if it has been proved to you. But if you know linear algebra, this formula can be proved quite easily. Okay? So let's talk about some linear algebraic concept. So we go back to the node voltage method. In node voltage method, what we do then is to so you have first assign voltages, assign node voltages. Okay? Apply KCL at every node. And then solve the equation involved. So in linear algebra, if the number of unknowns is equal to the number of equations, then the problem is solvable. Okay, this is number of equations. So when you assign node voltages, you have V1, V2, V3. For a general circuit, you might have n nodes to assign node voltages to. And then when you have assigned node voltages to a very complicated looking circuit, it can be n nodes, very complicated, but each node has a voltage that you have assigned to some node voltage, okay? Then you're at this stage of the problem. Then the next stage, you apply KCL at every node. And you apply KCL maybe in terms of V1 minus V2 over R1 or something like that, and then V2 minus V3 over R2 plus something, and then Vn minus 1 minus Vn over Rn is equal to 0. You have an equation like this, but you have n of them. You have n of these equations. Okay? So you have n linear algebraic equations. But some of the V's are voltage sources. Okay, some of the V's are voltage sources. For instance, if this is a voltage source, this V3 is not an unknown, it will be given the value of Vs. Okay, it's a known quantity. And that might happen, or maybe I can call this V2s. It's a known quantity. And some of the equations down there, you might have V3 minus V3s over R3. And then another equation down there, you might have a current source. You might have plus IS1 over there. And you have n of this equation. The next thing you should do is to put the known quantities to the right-hand side of the equation. Okay, all these are known quantities. These are known quantities. These are known quantities. You put them on the right-hand side of the equation. So what you have then is a linear algebraic equation. They look something like this: a matrix system, and with the node voltages V2, V3, V4. Okay, V maybe M or something. Maybe you have M voltages, and then you put all the known sources V1s, V2s, maybe something like IS1, IS2, and so on. This might be divided by R1. This might be divided by R2. Okay, so you have a linear algebraic equation, a set of equations where the right-hand side is known, the left-hand side is unknown. Okay, so at this stage you have an equation that looks something like A dot B is equal to B. B is known, B is unknown, A is known. Okay, how do we solve this linear algebraic system? V is equal to A inverse dot B. Okay? And you can say that you can find the inverse by the computer program or some of the clever technique you learn in class. It can be a 2 by 2 matrix system, then you can find it very easily with your hands. But if it's n by n, you don't do that with your hand, you do that with a computer. Okay, so I can say that this is K, a matrix K, times B. So if I take any element of this unknown vector, say Bi, the ith element, it must be equal to Ki1 B1 plus Ki2 B2 plus something else, okay? Kin Bn. Where the B's are some of these elements over here. You can see that any voltages that you have inside your circuit node is a linear superposition of all the known sources you have in the system. And that proves this statement. Okay, that proves this statement over here. And that means that any voltage that are unknown in the very beginning are linearly dependent on all the known sources you have in the system. Okay, this fact can be proven by linear algebra, and it's a linear superposition. You can solve this problem by turning off these current sources one by one, making the problem simpler. Okay, and then you can turn them off again and on again, and then there's a method of linear superposition. If you have two current sources or two sources inside, you can solve the problem one after the other one by turning on only one source and turning off the other one. Okay, turning off the current source means setting it to 0, which is like making an open circuit. Turning off the voltage source is like sending the voltage to 0, which is like making a short circuit. Okay, that's what it means. Okay, this is the understanding of the principle of linear superposition from the viewpoint of linear algebra. Okay, and many of you know linear algebra, and you can see, you can look at this problem from a higher level, and you can see that you have a different understanding of this problem. Okay, are there any other questions? I have 2 minutes left. Yes?
Your relationship supernodes, supergroup, and superposition.
Supernodes are nodes connected by a voltage source. A voltage source actually behaves like a short circuit, other than the fact that it has a voltage drop across the two points. So when you see two nodes connected by a voltage source, it's almost like the two nodes are connected by a short circuit. Okay? Any currents that flow into the voltage source must also come out of the voltage source. So you can consolidate the two nodes into one supernode. And current supernodes are intercepted by current source, which behaves like an open circuit. No current flow, no current flow.